Good day. So in this video, we're going to show a couple of examples involving derivatives of single variable functions. Now, the presumption here is that you have already viewed the rules of differentiation, which is already available in your slide packet. But of course, the rules are pretty straightforward. So what we're going to do here is to show a couple of examples that combine these rules of single variable differentiation. All right. So it's pretty straightforward. It's quite easy so long as you have mastered the rules of differentiation and so long as you have mastered the basic rules of algebra or basic rules of evaluating or manipulating algebraic expressions. So let's start off with a couple of simple functions like this one. So what if you're given with y is equal to log of x plus 3x minus 2. All right, so that's pretty straightforward. If I were to ask you to get the derivative of this function, like dy over dx, or in other expressions, you can get this as y prime, or if we defined y as f of x, then that's going to be f prime of x. So using the rules of differentiation, the derivative of this y expression would be 1 over x, right? Because of this, 1 over x plus 3, right? Because of power rule. So 3x becomes 3 because of power rule. X is raised to 1, so 1 x raised to the first power minus 1, that becomes x raised to 0, and that reverts to 1. So you just end up with 3. 2 is a constant, so since 2 is a constant, the derivative of a constant is automatically 0. Right? Now, what if we have, say, x squared, y is equal to x squared minus 2 ln 2 ln x, or 2 log of x, right? So again, that's also straightforward. So dy over dx, meaning the slope of this function, would be 2x minus, right, 2 over x. Okay, now that's pretty simple, right? Now, what if we have a fraction, right? What if we end up with y equals log of x over, of course, over x, right? So two ways. You can either use the product rule by using some simple manipulation, or you can use the quotient rule. All right. Now, on a personal preference, personally speaking, I prefer using the product rule because it's easier to evaluate. All right, it's easier to evaluate, and it's also pretty straightforward. So if we convert this into something like this, so x raised to -1, all right, so you'll have to master all of this. So if you get a fraction that's, say, 1 over x, if you get a rational expression, sometimes it's easier to convert it into its exponential form. All right, so you have x1 times log of x. Okay, or well, in practice, I tend to interchange log with ln. Even in statistical software, log is already synonymous, or it's already analogous to the natural log. So along this application, when we say log, just to be clear, when you say log in this application, we are referring to the function's natural log. Okay, so we have two functions. Basically, log x over x implies that we have two sets of functions, right? We have x raised to -1, all right, multiplied by the function log of x. Now, so since we have a product of two functions, we will use the product rule. So recalling the formula for the product rule. So say this is your function. So suppose y is a composite or a product of two functions, say f of x and g of x, right? Product rule states that you take the first derivative, or you take the derivative of the first function, right, times g of x plus f of x times g prime of x. So using this formula, using this rule, it implies that we'll get the derivative of x raised to -1 first times log of x plus f of x, which is x raised to -1 times the derivative of log of x. So dy over dx in this case would be negative x squared, right, by power rule times log of x plus x raised to -1 times 1 over x. All right. Now we can simplify this. So this becomes a negative log of x over, sorry, log of x over x squared. Right? Notice that the negative sign disappears because basically when you have a negative sign here, turn this into a fraction. All right. That's basically a fraction. So that's 1 over, that becomes 1 over x squared. Okay. Okay. Or it's tantamount to dividing 1. It's tantamount to dividing x raised to 0 by x squared. Hence the x squared term here. Right? So plus, so you have plus x raised to, or let's convert it to its fractional form, x 1 over x times, right, 1 over x, right? And that becomes 1 minus log of x over x squared, right? It's 1 minus log of x over x squared, okay? Now, as a matter of exercise, maybe you can use the quotient rule instead to verify that we got the same or you got the correct answer. Right. Now let's move on to more complicated functions. No, of course, all of these involves exponential and log functions. So what if we get something like this? Suppose we have y. Suppose you have y, or let's not apply y. Suppose you have an expression ln e of x plus 1. Right. Now, just a gentle reminder, if you see an expression like this, right, ln e of x plus 1, it just indicates that you're taking the log of this, and basically this is a log function whose arguments are ex plus 1. So the arguments will be a function, another function. So it's kind of similar to ln. It's kind of analogous to having ln as another function. Right? It's an ln of another function. Okay. So ln f of x, right? So based on our rules of differentiation, if we wanted to get the derivative of this expression, let's denote this as f of x, right? And just to be clear, let's denote this, let's try to denote this as g of x. Right? Now to get the derivative of that composite function, g of x, right, we'll need to apply the chain rule. Right? Chain rule indicates that if you have an outer function like so, you take the derivative of the outer function and then take the derivative of the inner function. So basically, we're getting something like 1 over ln f of x, right? So f of x is basically ex plus 1, right? Or maybe if you wanted to be more clear, that becomes ex plus 1, right? And then you multiply it with the derivative of the inner function, right? So what's the derivative of the inner function, right? So the derivative of the inner function would be ex, all right? The constant cancels out. Take the derivative of an exponential function, this natural exponential function, and you still get e of x, okay? Pretty straightforward, right? Another example, suppose we have, let's see. Suppose you have a rather more complicated expression like y as a function of log of 3x minus 1 over 1 minus x. Okay? So to get the derivative of this expression, right, let's say this is dy over dx. So that would be 1 over another fraction, which is 3x minus 1 over 1 minus x, right, times the derivative of the inner function. So what's this inner function, right? We can set this aside for a moment, right? Let's set this aside for a moment and let's denote, uh, to avoid confusion, let's denote g of x, right? Let's denote the inner function to be g of x, and let g of x would be 3x minus 1 over 1 minus x. Okay, then the derivative of that inner function, or equivalently, that's equal to, again, matter of personal preference, but if you wanted to use quotient rule, that's also fine. So that's 3x minus 1 times 1 minus x raised to negative 1. So you have two functions here. You have two functions, and then, of course, you take the derivative, you can use the product rule. Or, well, we can also use the quotient rule. So g of x, right? So g of x would be, or g prime of x would be the derivative of the numerator, right? So 3x minus 1, take the derivative of 3x minus 1 with respect to x, and you'll just get 3, right? Times the denominator, 1 minus x, minus 3x minus 1 times the derivative of the denominator. So that's just negative 1, right? That's just negative 1, okay, over 1 minus x squared. Okay? And this is equal to 3. Okay, maybe you can rearrange some terms later on. So you have 3 minus 3x. Basically, this is negative 1, so that's just plus 3x minus 1, okay, over 1 over x squared. Right? In case you're wondering why you have 3x minus 1 here, you have a negative 1 here, right? And you have a negative 1 as its a factor, right? You multiply this with negative 1 again here, and you'll have 3x plus 1. Negative sign cancels out. You're just left with 3x minus 1. Right? So 3x cancels out. You can subtract 1 from 3, and then you'll get 2. Get 2 over 1 minus x squared. Now we can plug this back in the earlier expression, the previous expression, in our original function. So you take the derivative of this, and then you'll have what? You'll have, oh, no, not equal sign. So you'll have another fraction. So that's basically 2 over 1 minus x squared. Okay. And I think we can cancel some terms out. So you can cancel this 1 minus x cancels out, right? And then you're just left with 1 over 3x minus 1. Let's try this. Dot. Oops. Sorry. I'm slowing down. Okay. C dot. Right, another fraction. So you'll cancel 1 minus x. And just becomes 1 minus x. Right, 1 minus x, and you'll have 2. So that would be the derivative of log 3x minus 1, log the function of 3x minus 1 over 1 minus x. Okay. Now, let's have a couple of examples involving polynomials. just in case you might find this log function a little too daunting for you. But of course, using log functions or using composite functions like this one allows you to practice the rules of differentiation, right? Because you're not gonna lose it. You're still gonna use those simple rules of differentiation as you go through more complex or more complicated functions like so, right? So suppose we have um, suppose you have let's see here. Mm, all right, suppose we have suppose you have z, you have function z, which is composed of squared u squared minus 1 cube, all right? And suppose you have another function u, right? So the function here, right? So it's a composite function again. So you have u as a function of the cube. Now, what if I ask you to get the derivative of dz, or the derivative of z with respect to t, right? What if we have that expression? Now, one straightforward way to do things, right, is to plug u right ahead in the function. So z, basically z as a function of t will become, right, and given the expression for u, then z as a function of t will just become u, or sorry, t cubed, right, squared minus 1 cubed, right? And that looks a little slightly easy, slightly simpler, because you'll just have a function of you'll just have z as a function of t, right? You don't have any other expressions, and if you're asked to get the derivative of z with respect to t, it's just a matter of looking at where t is, and then looking at the entire function and obtaining the derivative. So here we have an exponential function, right? Or you have an expression raised to the third power, so we'll need to use the chain rule. So you have 3, the inner function remains as is, or you want to distribute this, so t3 squared, right? T3 squared becomes t to the sixth, right? Minus 1 squared, right? Now multiply that, oops, you multiply that with the derivative of the inner function. So what's the derivative of the inner function? Right? The derivative of the inner function will be 6t raised to the fifth power. So that's your application. That's an application of chain rule. Now, what if we have some economic example, or something that resembles a function in economic theory, right? So suppose you have something like x. Suppose you have something like x, which is a function of a. Right? Let's denote this as x of. Sorry, let's denote this as probably z t raised to alpha, or a alpha, yeah, And another function here, let's denote this as wt, okay, raised to beta. Okay. Now, what if I ask you to get x dot, or in macroeconomics, you call this the change of variable, the change in the variable across time, or basically dx over dt. So what if I ask you to get dx over dt given this expression? Now, you have two functions. You have two functions, z of t and w of t, embedded within the expression for x. So again, this is just a matter of, using, uh, it's just a matter of using chain rule. It's just a matter of using chain rule in solving for the derivative of this expression. Okay, so let's do that. So notice that we have a product of two functions here, z of t of alpha, wt of beta, but of course, both of them are functions of x, right? So it's going to be a little straightforward. It's going to be easier. No? We'll just use the product. We'll just use the product rule. Okay. Now to go for the product rule, so let's begin by, say, looking at the first expression. So that's going to be alpha. Right? Let's say that alpha. Let's say that a belongs in the first function. All right. So to get the derivative of x, this expression of x with respect to time, we'll just have to use the product rule. Now, to make it easier for you, we'll just concentrate on these two functions here, right, and uh, apply differentiation. All right. So this is the first function, right, the first function, and then we'll need to, this is the second function. So basically, you will get an expression like this. So you have a. This is going to be slightly long expression. You can just ignore a because that's just constant. So that's a uh, times the derivative of the first expression. Right? So that's going to be a, or that's going to be alpha z of t, okay, raised to alpha. Okay. Now, how about minus one? How about the negative? How about the inverse of z of t, which is obtained by using the power rule? So we can just go and set it as the denominator already. So that's just z of t. Okay, z of t times the derivative of the inner function, right? Times the derivative of the inner function, which is z prime of t. Okay. So that's the derivative of z of t raised to alpha, right? And we still need the second expression. That's going to be w of t raised to beta over zt. Of course, that doesn't end there because we still need to get the derivative of this product with respect to the second function, right? So that's going to be, of course, similar to the first case. We have wt as a denominator, obtained by taking the derivative of w of t raised to beta with respect to t. So that's going to be beta w of t raised to beta, right? And you still have the first function, right? So that's going to be z of t. It's going to be z of t raised to alpha. Now we can combine this, right? Or you can combine these two, but of course you can just leave it as it is. Now, in macroeconomics, normally we're not just interested with the change in the variable across time. We're also interested in the growth rate. Now, to get the growth rate, of this expression, right, we'll need to divide both sides by x. All right. And now, when you divide both sides by x, you have to take into account that x is equal to this expression. Now, look closely, and we can actually factor out z of alpha, z of t of alpha, and wt of beta. Right. So that's a common term here. So if we take out that x, sorry, that's we take out that x, we factor out that x, we'll get something like this. So that's going to be a times z of t raised to alpha times w of t raised to beta. Where does this come? Where do these terms come from? We basically factored out z and w out, right? So you have z of t of alpha here, you have w t of beta here, you have z of t of alpha here, you have w of t raised to beta here. You can just factor them out, and then you'll end up with this expression, right, which is alpha z prime of t alpha z prime of t over zt plus beta beta oops beta w of t prime. Oh, I forgot, there's supposed to be a wt prime here in between, right? So there's going to be w prime of t, right? So you have w prime w prime t in this numerator, and you'll have w of t in the denominator. So that's your cleaner version of x dot or dx over dt. Now, if I ask you to get the growth rate of an expression, you'll need to divide this x dot by x, right? And what is x in the first place? X is equal to a of z of t, a times z of t raised to alpha, and w of t raised to beta. And if I divide both sides by x, this first term will basically cancel out. And therefore, x dot, right, the growth rate, x dot over x will be equal to solely this bracketed term. Okay. Oops. Cancel out, and this will just be equal to this bracketed term. Right? So that would be the growth rate of this function. So a matter of application, if you look at this closely and you pause the video for a bit, you can see how we applied the product rule, right? You can see how we applied the product rule and the chain rule in just one function. And that should be, it looks quite daunting at the start, but it should be straightforward. It should be a straightforward exercise. Okay, and maybe we can have another example. Maybe we can have another example. Something that would be interesting to you, and it's something that a little recursive. It could be a little recursive because we will introduce limits again, right? And this is where we see some examples of applying Lopital's rule, right, in evaluating limits, right? Now, before, in our previous lecture video where we talked about limits, there are certain limit functions, or there are certain functions that cannot be evaluated by simple factoring or by simple rationalization of a quotient of two functions. There are times that you will end up getting indeterminate or functions in indeterminate forms. So when we say indeterminate, if a function is indeterminate, it just means that when you apply the rules of limits, you will either get something like 0 over 0 or infinity over infinity, right? So let's just be clear that the L'Hopital's rule applies only if you have an indeterminate form, meaning you have 0, you'll end up getting a 0 over 0 or infinity over infinity. Now, how do we resolve that? How do we use L'Hopital's rule to to solve problems with to solve functions with indeterminate forms. So let's look at some examples, right? So say you have x, or the limit of, say you're asked to get the limit of x minus 1, x minus 1 over x squared minus 1 as x approaches 1. A closer look at this function indicates that we have an indeterminate form. Say if you substitute 1 and 1 in the numerator and in the denominator, you get a 0 over 0. Of course, if you're already comfortable in your college algebra, or you're already comfortable factoring form or factoring products like this one, you could argue that we can just easily say factor the denominator, cancel the numerator out, right? And of course, you'll get an expression that is 1 over x plus 1, and you'll know that the limit is equal to 1/2. Of course, that's perfectly fine. But if you're not comfortable factoring, or if you're not comfortable doing some mathematical manipulation in the first place, then we can use L'Hopital's rule. Now, what is L'Hopital's rule? You already have it in your slides. It just basically what we're going to do is, if you have an indeterminate form, you'll just get the derivative of both the numerator and the denominator, right? So let's use L'Hopital's rule. L'Hopital's rule. So to get the limit of this function, you can get the derivative of the numerator and the denominator. So that's going to be the limit of, what's the derivative of the numerator? The derivative of the numerator, oops, the limit of the numerator, the derivative of the numerator would be just what? With respect to x, that's just going to be 1, right? What's the limit of the denominator, right? Or sorry, what's the derivative of the denominator? That's going to be 2 over x. So you will continuously differentiate the numerator and the denominator so long as you have the indeterminate form, right? You'll only stop if the expression now becomes if the function stops being an indeterminate expression. Here, noticeably, we can now plug in 1 without any problems. And of course, the limit, as we have seen before, by factoring the denominator and canceling out the numerator and the denominator, the limit is equal to 1/2. Now, what if we have, well, let's try a more complicated example. What if we have, right, so let me just copy this so that everyone can see what we are doing. Right. So what if we have an expression like this one? So suppose you have the limit of ln. So notice that the limits, or L'Hopital's rule, is very applicable. It's very helpful if you have rational expressions like this one. And besides, this is only type of, normally this would be the type of function wherein we'll be encountering problems, wherein we'll encounter problems, especially if the function becomes undefined because of how the limit is defined. So for instance, we have this expression, right? ln of x over x, right? So the derivative, when we let x approach infinity, both the numerator and the denominator will approach infinity. But of course, it doesn't mean that the function doesn't have any limits. So maybe it's just a matter of manipulating this expression, right? So of course, we cannot do some further factoring here. We cannot do some further algebraic manipulation in this case. So we'll just use L'Hopital's rule. So when you use L'Hopital's rule, you get the derivative of the numerator and the denominator. So you'll have 1 over x over 1, right? Or simply 1 over x. Right? Let me just put the limit function here. Right? So as x approaches infinity, right? And this is simply the limit of limit of 1 over x as x approaches infinity, right? Now, the 1 over x is no longer an indeterminate form, and you'll have to be very careful with that, right? Because you can only use L'Hopital's rule if you have an indeterminate form. Now, 1 over x is not indeterminate because your numerator is a constant. It will never be equal to 0 or infinity, right? Only the denominator is equal to infinity. So you cannot use L'Hopital's rule. And here, the limit of x raised to x, limit of 1 over x as x approaches infinity will just simply become 0, right? Just simply become 0. And I can show that we can prove that, or you can show that using probably a mathematical software for you to verify that, well, or you can use a spreadsheet actually to verify that the function ln of x over x will just approach 0. Okay? Will just approach 0. It also indicates that when you have ln of x over x, your denominator grows, basically your denominator grows faster, it increases faster in scale than your ln of x. So in effect, when this grows faster, your entire expression will just approach 0. Okay. So let's have another example. What if we have, let's see. Let's see. How about how about 2 minus x 2 minus x 2 minus x e raised to x minus x minus 2 over x as x approaches 0. So normally, or when you look at this expression, you'll see that both the numerator and the denominator will be approaching 0. So it's an indeterminate form. Okay, so this becomes 0. So you have 2 e raised to 0 is 1. So 2 minus 0 minus 2, and you just have 0. So we'll need to use the L'Hopital's rule 3 times, right? So let's take the derivative. Let's take the derivative of the numerator in the denominator. So you'll have, right? So let's this is basically equal to the limit of, if you take the derivative of this expression, you'll have for the first product here, you can use the product rule. So you'll have negative e to the x, right? E to the x minus or plus, right? 2 minus x e to the x, right? Minus 1, right? Where's your minus 1 coming from? You take the derivative of this negative x here, you'll get negative 1. 2 cancels out, all right? over 3x squared as x approaches 0. Now, of course, if I still substitute 0 over 0 here, or sorry, if I substitute 0 in the numerator, in the denominator, you still get an indeterminate form, right? You can actually see here that when I substitute 0, so you'll have -1, you'll have uh, you have 2, right? You have 2 here. This becomes 2 minus 1, 1 minus 1 becomes 0, and of course the denominator is still 0. Right? Now you take the L'Hopital's rule, do the L'Hopital's rule again, and you'll get the limit of, you take the derivative of the numerator and the denominator with respect to x. Let's start with the denominator because that's straightforward. You'll get 6x, right? Now, if I take the derivative of the numerator, you'll get negative e to the x, right? You have e to the x plus, again, this needs product rule. You need to do product, or you'll need to do the product rule again. All right, so you'll have negative e to the x, all right? You have e to the x plus, right, 2 minus x e to the x over 6x over 6x, right? As x approaches 0. Okay. Now, if I plug in 0 again here, of course, it's still, well, if you plug in 0 here, so you have 1, sorry, you have 0, you have 1, -1 minus 1, -2, all right? You have -2 plus +2 here because this just becomes 0 times 1, 0, right? So you have another 0 over 0. So you need to do the L'Hopital's rule again, okay? So this becomes, right? So for easier reference, you have the denominator. You can start off with the denominator first. So you need to apply the L'Hopital's. We're doing another round of L'Hopital's rule again. So you have 6x, so this becomes just 6, right? Right. So you have x approaches 0. This x approaches 0. The thing about, again, the thing about exponential functions is that it's just equal to e to the x, right? You take the derivative, you still get the same derivative, e to the x minus e to the x, right? Now, using, again, the product rule, you'll have another e to the x, right? We'll have another e to the x plus 2 minus x e to the x. All right. Of course, you cannot use L'Hopital's rule anymore. All right, you cannot use L'Hopital's rule anymore because, well, well, the denominator is now non-zero, or it's no longer equal to infinity. So all you need to do is just plug this 0 across all of these expressions. So you'll get okay, you'll get 1, -1 minus 1 minus 1 plus 2, right, over 6, right? So notice here that when you add these two together, this just becomes negative 2. So you get an expression of -1 minus 2 plus 2 over 6. And the limit is equal to 1 over negative 1 over 6. Okay. Again, just to be clear, you can only use L'Hopital's rule if you have an indeterminate expression. If you have an infinity over infinity, or you have 0 over 0. But again, the rules of differentiation sticks. Right? They remain the same across all of these examples. Okay. So in our next video, right, in our next lecture video, as for your reference, we're going to do probably just some more examples involving differentials for a single variable function, and then we'll start with the multivariable or the derivatives of the multivariable function. Again, questions will be addressed in our next tutorial session. Thank you so much.